Jai Hind. Myself Ravindra Kumar, AP in EN Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today I am presenting on the topic series and parallel resonance in AC circuit, and this is covered under the second unit, that is steady state analysis of AC circuits, and the subject is fundamentals of electrical engineering. Basically, this is intended for first year students who are taking this course in first year classes. So, in this we will discuss series and parallel resonance, what are those resonance in AC circuit and how the circuit behaves under these conditions. So, if we see it, these are the contents: series resonant circuit, that will be discussed under this, and parallel resonant circuit. So, first thing is we discuss what is resonance and then what is series resonant and parallel resonant circuits. So, if we say it, resonance in electric circuit, how can it be taken? Any passive electric circuit means which is containing passive elements like R, L and C. So, for the resonance condition, this circuit will resonate if it has an inductor and capacitor, that means L and C. If it is having L and C in the circuit, that time it will resonate. That means both the elements must be there in the circuit. Next condition is resonance is characterized by the input voltage and current being in phase, that means they should be in same phase, or the phase difference between them should be 0 degree. And then the driving point impedance or the admittance, that becomes completely real when this condition exists. That means this driving point impedance or admittance, that will be having only the real part, no imaginary part in that time. This is the condition for resonance. We will see it in detail. Like this circuit, here we are taking series circuit. So, here we can see this resistance R, inductance L and capacitance C. They are connected in series with this AC supply voltage source, and same current will go through all these three elements since they are connected in series. That is the property of series circuit or series connection, that current is same through all the elements which are connected in series. Now, suppose this supply voltage, that is represented by Vm angle 0 degree, that is in polar form. This is a phasor representation of this supply voltage. Now, the input impedance of this circuit, that can be written as Z equal to R plus J into omega L minus 1 by omega C. Since R is the resistance in this circuit, XL, that is inductive reactance of inductor, that is given by J omega L in phasor form or complex form. Similarly, capacitive reactance XC, that is in complex form written as minus J upon omega C or 1 upon J omega C. Anyway, we can write it, since 1 upon J equal to minus J. So, with the help of this, we have written this expression for impedance for this circuit, and then the magnitude of current which will be passing through the circuit or through the elements which are connected in the circuit, that will be given as magnitude is magnitude of voltage applied, supply voltage, that is Vm, this magnitude, divided by the impedance magnitude. The impedance magnitude can be written as under root of real part square plus imaginary part square. So, that is under root of R square plus omega L minus 1 by omega C whole square. Since R is the real part of it and omega L minus 1 by omega C, that is the imaginary part of this impedance. So, that way this is the impedance magnitude of this circuit. So, voltage upon impedance, that becomes current. So, that way we find it. Now, for resonance condition, as we have already discussed that for resonance condition, the supply voltage and supply current should be in same phase, or the impedance or admittance in the circuit, that should have only the real part. So, that means if we see it from here, when impedance will be having only the real part, that means this part. So, that time this imaginary part will become 0. So, that time we will have impedance resonance condition in this circuit, and for that omega L must be equal to 1 upon omega C. So, that will become the condition for series resonance, and that time we will get maximum current in the circuit, since impedance will become minimum equal to R only, and current will become maximum, that is supply voltage upon resistance, since the impedance becomes R only that time. So, this is the condition for resonance, omega L equal to 1 by omega C, and from this we can find omega naught, which is 1 upon root LC. This is the resonance frequency. So, omega naught is representing the resonance frequency of the circuit. So, this is the value of resonance frequency, and the unit for it will become radian per second. If we find it in terms of F, so that time the resonance frequency F naught will be given by omega naught upon 2 pi. Since F is given by omega upon 2 pi, so this will become 1 upon 2 pi under root 1 upon LC, and the unit for this will be hertz or cycle per second or second inverse. Anyway, so that will be the expression for resonant frequency for this series RLC circuit. Now, we see the characteristics of series resonance. If we find it or if we observe it, one is that capacitive and inductive reactances are equal. That is the condition applied for series resonance. Total impedance is minimum and is resistive, Z equal to R in case of series resonance, that we have observed. Since these two reactances, capacitive and inductive reactances, when they become equal, then the net reactance of the circuit becomes 0, X, that is equal to XL minus XC, and becomes 0 since XL equal to XC at the time of series resonance. So, the current becomes maximum since impedance becomes minimum. So, current becomes maximum due to minimum impedance. Phase angle between supply voltage and supply current, that is 0. That is the condition of resonance again. Due to this, power factor will become 1. And resonance frequency FR, we are writing it FR, R for resonance and F for frequency. So, FR is resonance frequency for series RLC circuit. So, this is 1 upon 2 pi root LC. This is the expression for resonance frequency that already we have obtained in the previous discussion that we have seen here. So, this is the expression for series resonance frequency. Other than this, some more important points in this, that series resonant circuit is also known as acceptor circuit, since it accepts maximum current at the time of resonance. That is the reason for this. Another important thing in series resonance, that series resonance is also known as voltage resonance. Reason being, the voltage across L or voltage across C, they are more than supply voltage, or mathematically we can write VL upon V, that is more than 1, or VC upon V, that is more than 1. That means, in other words, we can say it is the amplification of voltage across L with respect to supply voltage, or it is the amplification of voltage across C with respect to the supply voltage. That is why this series resonant circuit is also known as voltage magnification circuit, or series resonance, basically it is known as voltage resonance due to it. So, these are some important characteristics or important points which are observed in series resonant circuit. Further, some other things, this is the graph between resonance, between the frequency and current in a series RLC circuit. So, when frequency is minimum, like here if we see it at this point, then the current we can get like this, current is also minimum. When we increase the frequency, current increases simultaneously like this, and at this point the current is maximum since impedance is minimum, Z equal to R, and current is supply voltage magnitude upon impedance R. So, that is maximum current this time, and this is the condition for resonance. So, we get resonance frequency corresponding to this. Now, on this curve we locate these points, one is this point, another one is this point. At these points current is 1 by root 2 times of the current at resonance at these points. The current magnitude is 1 by root 2 times of the current magnitude at resonance, that we can see, and the power at these points will be half of the power at resonance. So, that means suppose I write power PR at resonance, then the power here will become PR by 2 at this point and at this point. So, that is why these points are known as half power frequency point, since at these points power becomes half of the power at resonance, and the gap between these 2 points, that is known as bandwidth, BW. BW is bandwidth, that is this, and this can be written omega BW, and that will be equal to omega 2 minus omega 1, where this omega 2 is known as upper half power frequency point and omega 1 is known as lower half power frequency point. Reason being omega 1 is less than omega naught, that is why it is lower half power frequency point. And omega 2 is more than omega naught, so that is why it is upper half power frequency point. So, we can say this bandwidth is a gap between upper half power frequency point and lower half power frequency point. Other than this, we can observe other thing. After this resonance frequency point, on increasing the frequency, again the impedance will increase, and due to the increase in impedance, the current will decrease simultaneously, and that is why this is the nature of the graph between current and frequency for series RLC circuit, that is observed from this. Now, other than this, the maximum power is delivered to the circuit, that is magnitude of voltage square upon resistance at the time of resonance. This is the maximum power, resonance power also we can write it, and at half power frequency point the power becomes 1 by 2 of resonance power, since the current is 1 by root 2 times of the current at resonance. So, now from this what we do, we can find the half power frequency points omega 1 and omega 2. How do we find it? Since the impedance becomes root 2R at the half power frequency point, since we see the current is at resonance is Vm upon R, and at half power frequency point this is the current Vm by root 2R. So, root 2R is the impedance at half power frequency points. So, what we do, we write root 2R equal to under root of R square plus omega L minus 1 by omega C whole square, since impedance at any frequency in RLC series circuit is given by this relation under root of R square plus omega L minus 1 by omega C whole square. So, on doing this, we can find the value of omega 1, which is equal to this expression, and similarly the value of omega 2, that is this expression, by solving this equation, From this we get the value of omega 1 and omega 2, that is lower half power frequency and upper half power frequency. So, these are these, and from this we can find bandwidth, that is omega 2 minus omega 1, and that will come out as R by L, radian per second, or this can be written F2 minus F1 also, upper half power frequency minus lower half power frequency, and that will be R upon 2 pi L hertz or radian per second. Other than this, we can also find, if we take geometric mean of omega 1 and omega 2, then this is equal to omega naught, which is resonance frequency of series RLC circuit. That can also be found from this. If we multiply omega 1 and omega 2 and take the root of that, that becomes resonance frequency. Or in other words, we can say that resonance frequency is the geometric mean of half power frequencies. So, bandwidth is this, that already we have discussed in the last slide, and from this we can also define quality factor, Q factor of the circuit. So, quality factor is given by omega naught L by R or 1 by omega naught RC, where omega naught is resonance frequency, and by putting the value of omega naught in this expression, omega naught we know that is given by 1 by root LC. So, the quality factor becomes 1 by R root L by C, and using this quality factor Q, we can also write that bandwidth is equal to omega naught upon Q, where omega naught is resonance frequency and Q is quality factor. We can find it that bandwidth will become omega naught is 1 by root LC and Q that is quality factor, that is 1 by R root L upon C. So, if we simplify it, this becomes R upon L, which is the bandwidth. So, these are all important relationships in series resonant circuit. Now, for example, we take this circuit and we want to find the resonance frequency of this circuit. So, here we have the one resistance and this capacitance, they are connected in series across this point and this point. And in parallel to that, in an inductor L that is connected. So, if we find the impedance of this circuit here, Zn, so that will be the parallel combination of inductive reactance L and series impedance of R and C. So, we can write it Zn equal to j omega L into R plus 1 by j omega C divided by R plus j omega L plus 1 upon j omega C. Since R plus 1 upon j omega C is the impedance of RC series branch and j omega L is inductive reactance of L. So, that is why when they are in parallel across this point and this point, then this becomes the Zn. On simplification, it comes out in this form. Now, if we want to observe resonance condition in this, we know at resonance supply voltage and supply current, they are in same phase relation, or the impedance of the circuit that will have only the real part, no imaginary part. So, what we do, the imaginary part of this impedance that should be 0 at resonance. So, that is why at resonance the phase angle of Z must be equal to 0. Since when imaginary part of the impedance will be 0, that time the phase angle of Z must be 0 also. So, by doing so, what we have, this is the impedance of the circuit that we have found already, Zn. Now, for resonance condition, the imaginary part of the impedance should be 0. So, from that we will get this condition, and from that, this on solving out, it comes out in this form, and from this, this is the resonance frequency of this circuit that we have observed for this circuit. This is the resonance frequency of this given circuit. So, that way we solve any complex circuit for resonance condition, that what will be the resonance frequency of that circuit. So, this is about series resonance. Similarly, we find parallel resonance. So, if we see it for parallel resonance, normally we observe for this circuit where R and L, they are connected in series in one of the branch, and in parallel to that branch a capacitor is connected, and this circuit is connected with supply voltage V and supply current is I in this circuit, which is divided in I1 and I2 in parallel branches. So, this is the circuit for parallel resonance. So, now if we draw the phasor diagram of this circuit, how can we draw it? Voltage across these two branches will be equal, since these two branches are connected in parallel. So, what we take? We take this voltage as reference phase or reference phasor, since voltage same for the two parallel branches. Now with respect to it, we take current phasors I1 and I2 for the circuit. So I1 current that will be lagging by angle theta 1 from voltage phasor, and theta 1 will be given by tan inverse omega L upon R. Since I1 is the current in RL branch, and RL branch is just like RL series circuit. So there the current I1 will lag from the voltage across the branch by some angle. That angle is suppose theta 1. So theta 1 is given by this. While the current I2 that will lead by 90 degree from voltage. Since in this branch only a capacitance is there, that's why I2 will be leading by 90 degree from the voltage applied. So this is the phasor diagram of this circuit. Now for resonance condition, the supply current I that should be in phase with voltage V. I should be in phase with voltage V. And for that, the condition is that we should have I1 sin theta 1 equal to I2. Since I1 sin theta 1 will be this reactive component of I1, and if it is equal to I2, so that time reactive component will be cancelled out and I will become I1 cos theta 1 only, and that will be the condition for resonance. Parallel resonance. This will be the condition for parallel resonance. So from this, if we find it, what can we write? I1 will be V upon under root of R square plus omega L whole square into sin theta 1. Sin theta 1 will be given by omega L upon under root of R square plus omega L square. And I2 will be given by V upon 1 upon omega C. Okay, since I2 is the current in capacitor branch, so that will be voltage upon capacitive reactance, which is 1 upon omega C. So on solving this, we will get L upon C equal to R square plus omega L whole square, and from this omega becomes under root of one upon LC minus R square by L square, where this omega is resonance frequency. So we write it omega R. Since this is due to the resonance condition we are observing here, so the frequency here is the resonance frequency, and that comes out as under root of 1 upon LC minus R square by L square. And from this we can also find the impedance of the circuit. The impedance of the circuit will be given by I equal to V upon ZR, where ZR is impedance of parallel resonant circuit, which is also known as dynamic impedance. Parallel resonance. And this is also known as dynamic impedance. And if we calculate it, this ZR will come out as L upon CR. Reason being, how we find it? ZR will be given by V upon I, supply voltage upon supply current, which can be written V upon I. We have found it is I1 cos theta 1. So I1 cos theta 1 means V upon under root of R square plus omega L whole square into cos theta 1 means R upon under root of R square plus omega L square. and on simplification it will come out equal to R square plus omega L whole square divided by R. And here we have seen that R square plus omega L whole square equal to L upon C. So we put the value here L upon C divided by R. So on simplification it comes out as L upon CR. So this is dynamic impedance of this parallel resonant circuit. That way we find it. So this is the method for calculation of dynamic impedance of this parallel resonant circuit. Now another example for parallel resonant circuit we can take, like suppose the circuit is having R, L and C, they are connected in parallel branches. And for this circuit we want to observe the condition for resonance. Supply voltage V, supply current is I, it is divided in these three branches IR, IL and IC, since they are parallel branches. So if we draw the phasor diagram for this circuit, voltage will be taken as reference, since voltage will be same for all the three branches since they are in parallel. Now the current in resistance, that will be in same phase with voltage. This is the property for resistance. While in inductor, current will be lagging by 90 degree from the voltage. This angle is 90 degree. Similarly, in capacitor, the current will be leading by 90 degree from voltage. That is the property of capacitor. Now for resonance condition, we know supply voltage and supply current should be in same phase, or power factor must be 1 for resonance. Either it is series resonance or parallel resonance. So here for supply current should be in same phase with voltage. That means IL must be equal to IC, so that I will be equal to IR only, and it will be in phase with voltage, and due to it power factor will be 1, and we will get the condition for parallel resonance. Now for this we will have V upon XL, which is the current in inductor branch, and IC is V upon XC, that is the current in capacitor branch, or we can write XL equal to XC. That will be the condition for parallel resonance here in this circuit. And from this we can write omega R into L equal to 1 upon omega R into C, or omega R equal to 1 upon root LC. So this will be the parallel resonance frequency for this circuit. So depending upon the circuit connections or circuit configuration, we can find the condition for parallel resonance, and then the resonance frequency and impedance of the circuit, which is known as dynamic impedance in parallel resonance. Here if we find dynamic impedance will be ZR, which is the impedance at parallel resonance, that will be equal to R only, since supply current is in phase with voltage and that is equal to IR. So that's why the dynamic impedance will be equal to R only, since IR will be given by V upon R, and this is equal to I also. So that's why we can write it V upon ZR, which is the impedance of the circuit at resonance. So ZR will be R only in this case. So this is the condition for this circuit. Now if we see some important points related to parallel resonance, we can say it. The parallel resonant circuit is also known as rejector circuit or anti-resonant circuit. Reason being, this circuit rejects the current, only takes the minimum current at resonance. So that's why this parallel resonant circuit is also known as rejector circuit or anti-resonant circuit. Other than this, since the circulating current between the two branches is many times the line current, that's why the parallel resonant circuit is also known as current resonant circuit. That means to say we can write IC upon I is more than 1, or RL upon I is more than 1. That means the current in capacitor branch is more than the supply current, or current in RL branch is more than the supply current. So, that way it is the amplification of current. So, it is known as current resonant circuit due to it. And one more important thing, this parallel resonant circuit is also called tank circuit. So, these are some important features or important points about parallel resonance, that this is just opposite to series resonance. That is why it is known as rejector circuit, since series resonant circuit is known as acceptor circuit, and the reason for that already we have discussed, that series resonant circuit accepts maximum current, while the parallel resonant circuit accepts minimum current only. It rejects all the other currents. That is why it is known as rejector circuit, or also we call it anti-resonant circuit due to it. Series resonant circuit is also known as voltage resonant circuit, while the parallel resonant circuit is known as current resonant circuit. Since in series resonance voltage amplification takes place, while in parallel resonance current amplification takes place. Plus, parallel resonant circuit is also known as tank circuit. So, these are some important features, or we can say comparative points between series and parallel resonance. So, this is all about this. In the next lecture, we will discuss the next topic. Thank you for that.